Good morning, ladies. Today we are starting our next section, and this is all about mole calculations. The first thing that you need to know is that the mole is our SI unit for amount of substance, and SI just means it's the international system of units that we use. According to your guidelines, the mole is defined as the amount of substance having the same number of particles as there are atoms in 12 grams of carbon-12. And hopefully you can still remember from last year, this number that we're talking about is that 6 times 10 to the power of 23. So if I have 12 grams of carbon, how many atoms have I got? 6 times 10 to the power of 23. And that number is also referred to as Avogadro's number. The symbol for that you can see over there. And Avogadro's number is described as the number of particles present in 1 mole. Now these particles can be atoms. Hopefully you can still remember this as well. If we are busy with an element, the particles are going to be atoms. If we are busy with a compound, the particles are going to be molecules. And if it's an ionic substance, the particles will be formula units. And here is Avogadro's number, 6,023 times 10 to the power of 23. Last year we rounded off and said 6 times 10 to the power of 23. This year you'll actually use, because we round off to 2 decimal places, you'll use 6,02 times 10 to the power of 23, and that will appear on your data sheet. Let's take a look at our formulas. So this one is where we relate moles and mass, and I know we used it in our previous section when we were busy with the ideal gas equation, but let's just take a look at this again and remind ourselves exactly how this works. So N is equal to M divided by capital letter M. Your N is your number of moles, small m is your mass in grams, and capital letter M is your molar mass in grams per mole. This is what your triangle will look like, and as you know by now, that doesn't appear on the data sheet. Your formula will appear on the data sheet. And your molar mass is, of course, your value that you get from your periodic table, but we'll look at that just now. And then also, just according to the guidelines, your molar mass is defined as the mass of 1 mole of a substance measured in grams per mole, like we've already said. Exercise 8.1 is just to practice how to calculate the molar mass. So I've gone through the answers here. So if you want to try this on your own first, just stop the video, do the exercise, and then you can mark it. Let's take a look at this. So you'll find this on page 160 of your textbook. So number 1, you want to find the molar mass for hydrogen gas. So now you need to know that hydrogen gas is diatomic. So is H2 that we are looking at. So molar mass for hydrogen gas, if I look up the relative atomic mass for hydrogen on the periodic table, it's 1, but it's going to be 1 plus 1, which gives me 2 grams per mole. 1.2, we want to find the molar mass for aluminium sulfate. And aluminium sulfate is Al2SO43. I've done a little representation of it over here. Of course, it doesn't really look like this, but just to help, I've got 2 aluminiums, so there they are. So I look up aluminium's relative atomic mass, which is 27 times 2 plus, because I add together relative atomic masses. I've got 3 sulfates. So there's a sulfate, there's a sulfate, there's a sulfate. And each sulfate has 1 sulfur and 4 oxygens. So there's the sulfur, there's the 4 oxygens. So that is why it's going to be 3 times 32 for sulfur. I did that over there. And 12 times 16 for oxygen. There's 4, and there's 4. And that gives us 342 grams per mole. and then 1.3. We've got C12H22O11. So 12 times 12 for carbon, 22 times 1 for hydrogen, 11 times 16 for oxygen, and we get 342 grams per mole. Okay, then 2.1, calculate the number of moles. So N is what I want to work out. The number of moles of molecules in 15 grams of water. So number of moles, mass divided by molar mass. Mass 15, it is in grams like it's supposed to. I've calculated the molar mass for H2O over here. 1 plus 1 plus 16, which gave me the 18, which gave me 0.83 moles. Now here they say the number of moles of molecules. So this is my final answer. But because water is a compound and it consists of molecules, if it was calculate the number of moles of atoms, you would have done this, but then you would have multiplied your answer by 3 because one water molecule consists of 3 atoms. But yeah, they did ask for molecules, so that's our answer. Then 2.2, calculate the mass, so small m, of 0.05 moles of sodium oxide. So number of moles, mass divided by molar mass. Always the formula in its original form first. You can substitute directly into that formula or get m alone on one side first and then substitute, whatever is easier. So N, number of moles, molar mass, sodium oxide, 23 plus 23 plus 16, which gave me the 62, and that gives me the final answer, 3.1 grams. And then 2.3, calculate the number of moles of ions in 10 grams of magnesium chloride. So number of moles, mass divided by molar mass, 10 divided by, I worked out the molar mass for magnesium chloride. I got 95 and my answer was 0.11 moles. The question was the number of moles of ions in 10 grams of magnesium chloride. And magnesium chloride consists of 3 ions because there's a magnesium, there's a chloride and another chloride. So if I take that and I multiply that by 3, that is going to be my final answer. Okay, then also according to the guidelines, you must be able to state Avogadro's law. 1 mole of any gas occupies the same volume at the same temperature and pressure. And this is where we did this last year as well. We said at standard temperature and pressure, 1 mole of a gas occupies a volume of 22.4 decimeters cubed. I'm sure you remember that value over there. And then standard temperature, of course, is 0 degrees Celsius or 273 Kelvin. And standard pressure is 101.3 kilopascals or 1 atmosphere. So our molar gas volume is 22.4 decimeters cubed per mole. Now last year you just used the value, but since we've done our ideal gas equation, we can actually look at where that value comes from. Because if I say calculate the volume of 1 mole of a gas at standard temperature and pressure, and we use our ideal gas equation, which looks like this. PV is equal to nRT. Volume is going to be N times R times T divided by pressure. It's 1 mole, so it's 1. R is our constant, 8.31. Standard temperature is 273 Kelvin. Standard pressure is 101.3 kilopascals. But for the ideal gas equation, it must be pascals. So it's that value over there. The answer that I get is that. And when I'm busy with this, volume is in meters cubed. If I multiply by 1,000 to convert this to decimeters cubed, I get the 22.4 if I round off that we have been using all along. And then you can just make a note of this, just in case you come across something like this. A liter is equal to 1 decimeter cubed, which is equal to 1,000 centimeters cubed. and a centimeter cubed is the equivalent of a milliliter. Then some worked examples which you'll find in your textbook on page 161, although my answers are slightly different to the answers that you, or not the answers, the method is slightly different to the method that you've got in the textbook, because I wanted to show you that you could do this as well and get exactly the same answer as in the textbook. So we want to calculate the volume occupied at standard temperature and pressure by 1 gram of hydrogen. Now this formula you'll also recognize from last year. This is where we related moles and volume of a gas. And there's your triangle that you used. So molar volume, that is the 22,4 that we've been talking about. So volume will be moles times 22,4. I've got 1 gram, so I had to work out the moles, which I did over there. And I get 11,2 decimeters cubed as my volume. If I look at the second question, I've got 22 grams of carbon dioxide. Volume will be moles times 22,4. I worked out the moles over there and I got 11,2 decimeters cubed. And then number 3, now I've got 3,01 times 10 to the power of 23 molecules of nitrogen, and I want to work out the volume. And this is our third formula that we used last year, where we related moles and number of particles, and it looked like this. So I took this and I worked out the number of moles. I got 0,5 multiplied by 22,4, and I get 11,2 decimeters cubed. And this then shows us something very important. The same number of moles occupy the same volume at standard temperature and pressure. It doesn't matter what gas we're dealing with, because if we take a look at our first example, here we had hydrogen gas. We worked out that we had 0,5 moles and our volume was 11,2. In number 2, we had carbon dioxide gas. Again, we worked out we've got 0,5 moles, and what was the volume? 11,2. In our third example, we had nitrogen gas. We calculated the moles as 0,5, and what was our volume? 11,2. So same number of moles occupy the same volume at standard temperature and pressure. It doesn't matter what the gas is. What you can then do for me on page 162, exercise 8.2. Thank you, ladies.